Hello everyone, my name is Balagopal Komarathu and I am going to be presenting this work titled Rabbits Approximate, Cows Compute Exactly. This is joint work with Anurag Pandey and Nitin Saurabh. We will begin by looking at a famous sequence of numbers called the Fibonacci sequence, which is defined as f0 is equal to 1, f1 is equal to 1 and fn is the sum of fn minus 1 and fn minus 2 for n greater than 1. So the earliest historical record of this sequence of numbers is by Pingala, who used this sequence to count the number of patterns of n time units, where a pattern is composed of short syllables each of 1 time unit and long syllables each of 2 time units, and fn is exactly the number of patterns that will span n time units. For example, if you take n is equal to 3, then we have the 3 patterns S, 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 L and LS, and the Fibonacci number F3 is also 3. Fibonacci studied this sequence to model the breeding of pairs of rabbits. So the story is that pairs of rabbits breed to produce a new pair from the second month onward. So starting with a single pair, what is the number of pairs after n months? So it turns out that this is also exactly equal to the nth Fibonacci number. You can generalize this sequence of numbers into a sequence of polynomials, which is known as the continuant polynomials, and it is defined as k0 is equal to 1, k1 is equal to x1 and kn is xn times kn minus 1 plus kn minus 2 for n greater than 1. As can be easily observed, if you evaluate kn at the all ones vector, you get the nth Fibonacci number. This family of polynomials also has other interesting properties, such as the ratio of continued. So the ratio of these polynomials are continued fractions, and each polynomial in this family can be expressed as the determinant of a tridiagonal matrix. So for example, here I show how to express K4 as the determinant of a tridiagonal matrix of order 4. So notice that in here, the main diagonal contains the variables x1, x2, x3, x4. The diagonal just below the main diagonal is all ones, and the diagonal just above the main diagonal is all negative ones. So this equation can be generalized to express Kn as the determinant of an n by n tridiagonal matrix in a natural fashion. We now look at computational models that will compute sequences of polynomials. So one such computational model, which is very natural, is a formula or an expression that expresses a polynomial in terms of plus product, variables and constants. As an example, I give 2 different formulas for the same polynomial. So notice that 1 plus x1 times 1 plus x2 and x2 x1 plus x1 plus x2 plus x1 are 2 distinct expressions that compute the same polynomial. Now you can ask the question, which formula is better for computing this polynomial? So if you look at this formula, it uses 3 operations and this formula uses 4 operations. So one can say that the formula that uses the fewer operation is better. And for a given polynomial, we can define its formula complexity as the minimum number of operations required by any formula to compute it. Right? So the formula complexity of P is minimum number of ops to compute N, to compute P. We can also view the family of polynomials K as a computational model for computing polynomials. As an example, observe that k5 of x1 0, x2 0, x3 is equal to the polynomial x1 plus x2 plus x3. So notice that here I am substituting for the variables of k5 using variables or constants and nothing else. So I will not use arbitrary polynomials to substitute for the variables of k5, only variables and constants. And therefore you can view this as k5 being used to compute the polynomial x1 plus x2 plus x3. This can be generalized to show that the sum of n variables can be computed by k sub 2n minus 1. And using this, we can define the k complexity of P as the min index of k that computes P. So for example, if you look at this polynomial x1 plus up to xn, its formula complexity is n minus 1 and its k complexity is 2n minus 1. So it is slightly larger, but it is not much worse because they are related by a constant factor. So how powerful is the computational model which we call K? So in 2015, Allender and Wong showed that this polynomial x1, x2 plus x3, x4 plus etc. up to x15, x16, it cannot be computed by K. On the other hand, if you look at this polynomial, its formula complexity is just 15, or is at most 15, whereas its K complexity is infinite. Therefore, K is not a very good computational model for computing polynomials. But in 2017, Brigman, Mickenmeyer and Suida showed that any formula can be efficiently approximated by K. So this notion of approximation we are not going to define in this talk, but this particular result again shows that K is a good model to compute polynomials if you allow approximations. So in this sense, continuum polynomials can approximate every polynomial very well. In this paper, we look at this sequence of numbers called Narayana's curve sequence, which is defined like this: C0 is 1, C1 is 1, C2 is 1, and Cn is the sum of Cn minus 1 and Cn minus 3 for n greater than 2. So this sequence was first studied by Narayana Pandita, who used it to model the number of cows after n years, where cows are just like rabbits, but they only reproduce every third year. And Cn is the number of cows after n years. So for example, this sequence begins as follows: 1, 1, 1, 2, 3, 4, 6, 9. So this is a sequence of numbers that grows slower than the Fibonacci sequence, but it is still exponential, and it has other interesting properties in combinatorics. But in this talk, we are going to look at this family of polynomials which we call Narayana's curve polynomials, which is closely related to Narayana's curve sequence. So we define this sequence of polynomials as follows: G0 is 1, G1 is x1, G2 is x2, x1, Gn is xn times Gn minus 1 plus Gn minus 3 for n greater than 2. So notice again that Gn of Gn evaluated at the odd ones vector is just the nth number in the Narayana's curve sequence. One can also define this related sequence of polynomials: P0 is 1, P1 is 0, P2 is x1, and Pn is xn minus 1, Pn minus 2 plus Pn minus 3. So this is a recurrence where the nth term depends on n minus 2 and n minus 3 terms. So this family of polynomials comes from a number, comes from a sequence of numbers which is called the Padovan sequence. So we call it these the Padovan polynomials, and it is named after Richard Padovan. So the main theorem in this paper is that any formula can be efficiently computed by G and P. So if you view these sequences of polynomials as computational models, then they are equivalent in power to formulas. So here computation by these polynomials are defined as above. So we allow substitutions by variables and constants, and the efficiency is the min index of the polynomial in this family that computes the required polynomial. So if you are familiar with algebraic circuit complexity classes, we are basically proving that these two families are complete families for the complexity class Vf. Before looking at our proof, we will also take a look at the structure of some determinants and their associated complexity. So if you consider determinants of diagonal matrices, they have very small formulas. So the formula is just a product of the entries on the diagonal. But if you substitute for these variables with variables or constants, you cannot, for example, compute a polynomial like x plus y that has 2 or more terms. On the other hand, if you take the completely general family of matrices where each entry is a new variable, then Valiant in 1974 showed that every formula is efficiently computable by determinants of such matrices. On the other hand, we do not know whether small formulas exist for such determinants. So a natural question that falls out of this is how many non-zero diagonals are correct? Where correct means that f is reducible to this determinant family, and this determinant family also has small formulas. This is the question that we look at in this. This is one of the questions that we look at in this paper. So our main discovery is that 3 non-zero diagonals are enough. And the matrix or the family of matrices that we use is as follows. So the main diagonal is x1 to xn. The diagonal just below it is all ones, and the diagonal 2 steps above the main diagonal is again all ones, and the rest of the entries are 0. In fact, the determinant of these matrices are exactly the Narayana-Gauss polynomials, and if you compare it with the matrix for the continuant, for example, you can see that this matrix can be obtained from this matrix by taking this diagonal and shifting it by one place in the upward direction. Let's take a look at the proof. We denote by A of P, where P is a polynomial, the 3 by 3 matrix P01, 1, 0, 0, 0, 1, 0. And we can prove an intermediate lemma that allows us to show that Narayana-Gauss polynomials is exactly captured by a product of such matrices. So if you take the nth polynomial, then it's a product of A of x1, A of x2, etc. up to A of xn and taking its 1/1th entry. Now, to go from formulas to Narayana-Gauss polynomials, we just have to go from formulas to matrix products. So this is our main lemma, and we show that for any formula f with s operations computing some polynomial p, well, we can compute A of p as a small sequence of A matrices that only use variables and constants. So notice that the sequence on the right hand side has m matrices, and m is polynomial in the size of the formula. Also, each yi on the right hand side is a variable or a constant. So the proof is by induction on formula depth. We use the classic structural induction based definition for formulas. In the base case, a formula is either a variable x or a constant alpha, and in the inductive case, the variable is either a sum of two formulas or a product of two formulas. The depth is defined inductively. The depth of a variable or a constant formula is a 0, and the depth of the formula f of g is 1 plus max of depth of f, depth of g. So in the base case, the formula is a variable or a constant, and we can compute it using a sequence of A matrices of length exactly 1. So if it's a variable, you take A of x, and if it's a constant you take A of alpha, where x and alpha are the required variable and the constant. Now for the inductive cases, if you want to compute f plus g, then you can compute it as A of f plus g is A of f, A of 0, A of 0, A of g. So you can verify this by writing down these matrices and computing the product, and you will see that this is exactly A of f plus g. For the other inductive case, f times g, we have to work a bit harder. So we define a new kind of matrix, B of f, which is very similar to A of f. It is just that the f is positioned at entry 1, 2 instead of 1, 1. And if you compute the product B of f, A of 0, B of g, then you get this 3 by 3 matrix, which has the product of g and 3 ones, but they are in the wrong position, and there is also a spurious f and a spurious g in this matrix. So if you post multiply this with B of minus f, then the spurious f will get removed, and in order to remove this g, we can pre-multiply by B of minus g, and then to permute the entries of this matrix after all these multiplications to the correct position, we can multiply it by A of 0, A of 0. So notice that A of 0 is a permutation matrix. So now the problem is we have expressed A of fg as a sequence of A and B matrices. However, to prove the lemma, we have to show that this can be done only using A matrices. This can be done by showing that you can go from B to A. So B of fg can again be expressed as a sequence of A matrices using a similar idea. So we compute A of f to compute a matrix that contains fg, and then we multiply by A of minus g and A of minus f to remove those spurious f and g, and the remaining multiplications by A of 0 ensure that the entries are permuted into the correct positions. So this completes the proof of the lemma and our main theorem. So another interesting way to look at our result is to examine a parameter that is called the bandwidth of matrices. So what is the bandwidth of a matrix? So consider a matrix where the main entries contain some non-zero entries possibly, and you travel in the upwards direction diagonal by diagonal until you hit a diagonal such that all entries above that diagonal are 0. So call this distance between the main diagonal and this diagonal as k1. Similarly, you can travel in the downward direction until you hit a diagonal where all the entries below it are 0. So the bandwidth of this matrix is now defined as a max of k1, k2. Matrices with bandwidth 0 are just the diagonal matrices, and they are not very powerful even though they have small formulas. Matrices with bandwidth 1 are exactly equivalent to the continuant polynomials. They can approximate things efficiently, but they cannot compute things exactly. Matrices with bandwidth 2, as we saw in our proof, compute Narayana-Gauss polynomials. Therefore, matrices of bandwidth 2 capture the formula complexity exactly up to polynomial factors. And if you take any constant k bandwidth matrix, such matrices have small formulas which imply they can be expressed as Narayana-Gauss polynomials, which again imply that they can be brought down to bandwidth 2. Therefore, our result also shows that if you look at the computational power of the determinant in terms of the bandwidth, we hit maximum power at bandwidth 2 for constant bandwidth. So thank you for listening to this talk. We will take questions during the live session.